Hello everyone, hope you have gone through the previous video and understood what is the limit of a function and how to evaluate the limit. Let's see today what is to be done. Today, as again, we'll continue with differential calculus. In that, we are dealing with algebra of limits. Okay, so the objective of today's video is to understand the properties of limit of a function. And at the end of the video, you will be able to evaluate not only limit of a simple function plus a limit of some bigger functions also. What you need to know? You need to know the definition of limit of real valued functions. Okay, let's state this algebra of limits in the form of a theorem. The basic idea to give this theorem is, suppose I am given two functions. We have learnt how to find the limit of a function, right? Suppose I am given sin x plus cos x at x tending to 0. This is the limit I want to find out. I know how to find the limit of sin x as x tends to 0. We know how to find the limit of cos x as x tends to 0. Suppose I am given sin x plus cos x or sin x minus cos x, sin x into cos x. Then what should I do to find the limit of that particular function? That is what this theorem tells us. Suppose we are given two functions f of x and g of x whose limits at the point a we already know. Limit x tending to a, f of x is equal to L, and limit x tending to a, g of x is equal to M. This is already known to us. Then the following is true. What is true? Suppose I am taking f of x plus g of x. This is the new function and I want to find the limit at x tending to a. Limit at x is equal to a. Then I need to do, what do I need to do? I simply need to add the limit of f of x and the limit of g of x at x tending to a. Similarly, if I have f of x minus g of x, I know the limits of f of x and g of x at x is equal to a already. So, to find the limit of f of x minus g of x, I simply need to subtract the value of the limits. If I need to find the product of the limit of two functions, the limit of the product, then I simply need to take the product of the limit. If I need to find the limit of f of x by g of x, then I will take the limit of f of x divided by limit of g of x. This is a fraction, so we need to assure that the denominator is not equal to 0. Therefore, this limit x tending to a, f of x by g of x will be equal to L by m provided that m is not equal to 0. This is a very simple theorem. It looks very simple. This is what we use unknowingly. Without our knowledge, we will be using this theorem everywhere. Explicitly, we are going to state it in the form of a theorem. We will try to prove this theorem. Proof of 1. What is 1? I already know the limit of f of x. I already know the limit of g of x. I need to find the limit of f of x plus g of x at x tending to a. Before we begin with the proof, I will simply recall what is the epsilon delta definition. We say that limit x tending to a, I will state the definition for this limit. We will say that limit x tending to a, f of x is equal to L if given epsilon greater than 0, however small, we can find a real number delta corresponding to that epsilon such that whenever the distance between this x and a is less than delta, the distance between f of x and L, modulus of f of x minus L will be less than epsilon. The same thing will apply to this limit also. Given any epsilon greater than 0, we can always find a delta greater than 0 such that when the distance between this x and the point where I take the limit, distance between x and a becomes less than delta, then the distance between g of x and m becomes less than epsilon. Knowing this definition, we will proceed further with the proof. We'll start with the proof. I'll start with given f of x, the limit extending to a f of x is equal to L and limit extending to a g of x is equal to M. By definition, I already told now, limit extending to a f of x is equal to L means given epsilon greater than 0, there exists a delta 1. I will because I have two limits, the first delta I will call it as delta 1 and corresponding to the second limit with the same epsilon I will find another delta, that delta I will call it as delta 2. Therefore, given epsilon greater than 0, there exists a delta 1 greater than 0 such that whenever the distance between x and a, distance means in mathematical terms I will write it as mod x minus a, is less than delta 1 and greater than 0. I don't want it to be x equal to a. When I spoke about limits, I said limit simply means what happens when I come very close to this point. I am not bothered what happens exactly at this point. Okay. So, very closer means distance between x and a will be positive. X will never be equal to a. If x equal to a, then x minus a will be equal to 0. If x and a are same, then the distance is 0. So I am not bothered what happens when x and a are equal. I want when x is very close to a. Therefore, this condition is also important. Though it looks greater than 0, it doesn't matter much, but it is important for us. So, whenever the distance between x and a is less than delta 1, we have the distance between f of x and L is less than epsilon by 2. There are few things which you should observe, little different from the original definition we have taken. We have taken an epsilon, we have chosen some epsilon greater than 0. I took this delta 1 because we know that there are two limit definitions to be applied. So, for the first one epsilon I will take for both of them, I will take the same epsilon, and for the first one the delta what I get I will call it as delta 1, and for the second limit the delta what I get I will be calling it as delta 2. And here by definition modulus of f of x minus L is less than epsilon is what we have stated in the limit of a definition. But why epsilon by 2? I will come back to this epsilon by 2 later. I will call this as equation 1. Same way, similarly given limit extending to a g of x is equal to m. Therefore, for the same epsilon, I can find another delta 2 greater than 0 such that whenever the distance between x and a is less than delta 2 and greater than 0, we have modulus of g of x minus m. When x comes close to a, g of x comes close to m. That means the distance between g of x and m is less than epsilon by 2. Again, we have taken epsilon by 2 here, but why this epsilon by 2? We'll come back at the end. So, I'll call this as equation 1 and 2. Now, we have done this in the previous theorem also. I'll come back here. What does this say? When the distance between x and a is less than delta 1, this condition is satisfied. When the distance between x and a is less than delta 2, this condition is satisfied. Can I find a value of delta for which both these conditions are satisfied? Which conditions? Distance between f of x and L must be less than epsilon by 2, as well as distance between g of x and m must be less than epsilon by 2. So, what do I have now? I have the number line. Delta 1 and delta 2 are two numbers. Okay, this is delta 1 and this is delta 2. For distance between x and a less than delta 1, that means to this side, or rather to this side, distance between x and a less than delta 1, after this point to this side, the first condition is satisfied. Say delta 2 is here, okay. Behind this point, second condition is satisfied. Behind this point, first condition is satisfied. Behind this point, second condition is satisfied. Therefore, which is minimum of these two? Behind that point, both these conditions are satisfied. I hope you get this particular point. This is also an important crucial part in the proof. Okay. So, what I am doing is I will take delta is equal to minimum of delta 1 and delta 2. Okay. So, if I take a simple example, I will call this delta 1 as say I take a number as 2. Okay. I'll call this delta 2 as say 3, okay, or rather 1 and 2 we will take it. Say delta 1 is equal to 1 and delta 2 is a number 2, okay. When distance between x and a is less than 1, this condition is satisfied. When the distance between x and a is less than 2, this condition is satisfied. So this is less than 1, this is less than 2, okay. So if I take the distance is less than 1, anyway this condition is satisfied. If I take distance between x and a less than 1, this condition is satisfied until it is less than 2. So it is satisfied for less than 1 also. That means whatever is the minimum of these two numbers, when distance is less than that minimum, both the conditions are satisfied. So I'll call that minimum value as delta. Delta is equal to minimum of delta 1 and delta 2. Then from equations 1 and 2, whenever the distance between x and a is less than delta, both these conditions are satisfied. We will keep this aside now. Now we'll come to the main part here. What is the main part I want to prove? Okay, somewhere we have written the definition. If I want to show that limit extending to a f of x is equal to L, then what is that we are supposed to prove? We are supposed to prove that if I take any epsilon, I should find a delta such that when the distance between x and a is less than delta, f of x minus L should be less than epsilon. Now, what I want to prove is limit extending to a f of x plus g of x is equal to L plus m. Then what should I show? When the distance between x and a is less than delta, I want to show that the distance between f of x plus g of x and L plus m. I hope you understand. The distance between f of x plus g of x and L plus m should be less than epsilon. That means I want to talk about the distance means modulus of f of x plus g of x minus L plus m should be less than epsilon whenever the distance between x and a is less than delta. That is why after this part we have taken modulus of f of x plus g of x minus L plus m. Okay. Now f of x minus L, I will put it together here. G of x minus of m, I will put it together. We will try to apply the triangle inequality here. What does the triangle inequality say? Modulus of a plus b is less than or equal to modulus of a plus modulus of b. The a part I am taking here is f of x minus L. The b part is g of x minus m. This is modulus of a plus this part is b, which is less than equal to modulus of a plus modulus of b. Okay, and now this condition will come back here. What did we say? Modulus of f of x minus L will be less than epsilon by 2. Modulus of g of x minus m also will be less than epsilon by 2. When is this true? When the distance between x and a is greater than 0 and less than delta. That is what we have done here. Modulus of f of x minus L is less than epsilon by 2 whenever modulus of x minus a is greater than 0 and less than delta, and modulus of g of x minus m is also less than epsilon by 2. So epsilon by 2 plus epsilon by 2, this is equal to epsilon. So what did we get finally? Modulus means the distance between f of x plus g of x and L plus m is less than epsilon whenever modulus of x minus a is greater than 0 and less than delta. So given an epsilon, I could find a delta such that the distance between these two quantities is less than epsilon whenever mod x minus a is less than delta. That means by definition, what did we get? Limit x tending to a f of x plus g of x is equal to L plus m. This is the proof of the first part. Okay. So what about the proof of the second part? Second part, what do I have? Minus f of x minus g of x, and here it is L minus m. So what will you do? The first part is same. Instead of f of x plus g of x, I want f of x minus g of x and L minus m, and you see what happens with the definition. So proof of the second part, I'll leave it to you. You'll have to try it yourself, and I have given the hint also. It is same as the proof of 1. Try it. So proof of 3, what was 3? Limit x tending to a, f of x into g of x is equal to L into m. Okay. Now, proof is slightly different from the first part. We had taken some epsilon greater than 0, and we found corresponding delta such that whenever mod x minus a is less than delta, we will get f of x minus L is less than epsilon. Okay. But here I am not choosing any epsilon greater than 0. I will choose a particular epsilon which is anyways greater than 0, but also it is less than 1. My definition should work for any epsilon I choose. In particular, I am choosing an epsilon which is greater than 0 and less than 1, and I am calling it as not epsilon, epsilon 1. So, corresponding to this epsilon also we can apply the definition. Any epsilon I can apply. In particular, epsilon 1 less than 1 also I can apply the definition. Now, by definition, since limit x tending to a, f of x is equal to L, given this epsilon, this particular epsilon, for this epsilon I can find a particular delta 1 such that whenever mod x minus a is greater than 0 and less than delta 1, we have the distance between f of x and L. Mod f of x minus L will be less than epsilon. For this particular epsilon 1, I could find a delta 1 which satisfies this condition. Okay. Similarly, I am given the second limit, limit x tending to a, g of x is equal to m. Therefore, for the given same epsilon 1, I can find another delta 2 greater than 0 such that whenever the distance between x and a is greater than 0 and less than delta 2, we have the distance between g of x and m is less than epsilon 1. I have called it as equations 3 and 4. Okay, so what is the next condition? I want a delta for which both these conditions are satisfied. So what is the choice of delta? The delta is equal to minimum of delta 1 and delta 2. The delta is equal to minimum of delta 1 and delta 2. Then from these two equations, what do we have? Modulus of f of x minus L is less than epsilon 1 and modulus of g of x minus m is less than epsilon 1 whenever the distance between x and a is less than delta. Now in the previous proof I had taken epsilon by 2 and epsilon by 2. Now why here epsilon 1? We'll quickly go back. I told I will tell that to you at the end of the proof. Now here if I had taken epsilon and epsilon, when I add up I would have got it as 2 epsilon. It doesn't look nice with my definition, that's all. It doesn't give any problem. So if I had taken epsilon by 2 and epsilon by 2, when I add up at the end I will get this quantity is less than epsilon. So it looks like a standard definition. That is the simple reason why I have taken it as epsilon by 2. Other than that, if you simply take less than epsilon, it is completely true. You need not worry with anything. Okay, so we had come to this proof. So from 3 and 4 we have modulus of f of x minus L is less than epsilon 1 and modulus of g of x minus m is less than epsilon 1 when this condition is satisfied. Now there are few things which I need to work when I have a product. I will take this function g of x. I will talk about modulus of g of x. For the modulus of g of x, I will add and subtract m minus m plus m. Again by triangle inequality, I will split this. Mod a plus b is less than or equal to modulus of a. This is the first term what I will take. Modulus of a plus modulus of b. Okay. And what does this give us? By the definition of limit extending to a g of x is equal to m. What do I have? Limit extending to a g of x is equal to m. Modulus of g of x minus m will be less than epsilon 1 when mod x minus a is less than delta 2 and greater than 0. So modulus of g of x minus m will be less than epsilon 1 whenever modulus of x minus a is less than delta. And we had already taken epsilon 1 as a quantity less than 1, so that epsilon 1 is less than 1, and this plus mod m we have written it as it is. Okay. Now to the main part of the proof. We are talking about product. So what I need to prove, as x goes near to a, the product will go very close to L into M. So I am taking the distance between the product and L into M. Modulus of f of x into g of x minus L into M. We will know now why I took this modulus of g of x. F of x into g of x, I will keep it as it is, minus L into M also I will keep it as it is, and I am adding and subtracting two quantities, L into g of x minus L into g of x, plus L into g of x minus L into g of x. What is the trick in this L into g of x? Why only L into g of x? Okay, the trick is I am taking the limit of the first function into the second function. Limit of first function is L, second function is g. So I am taking L into g of x. You can work the other way around also. You can take the first function into limit of the second function also. But then with that you will have to do little changes. Okay. So what is the function I am adding and subtracting? I am taking the limit of the first function into the second function. That is L into g of x plus L into g of x minus L into g of x. Now we will group the terms. How to group these terms now? Okay, now the first term is L in f of x into g of x. I will group this with some common thing I should have. So I will group this with L into minus L into g of x, because we know the quantity f of x minus L. So the negative one I will take with the first term. So minus L into g of x I will take it with the first term, minus L into m plus L into g of x. The first two terms g of x is common, so take g of x common. What I am left with, f of x minus L. The second terms L is common, what I am left here, g of x, I will put this term the second part, g of x minus m is left here after taking L common outside. So mod a plus b is less than or equal to modulus of a, that is modulus of the first term plus the modulus of the second term. Now again I have a product of two terms inside the modulus. I hope you know the properties of modulus. Modulus of a into b, mod inside mod a into b, it is equal to modulus of a into modulus of b. So now this is modulus of AB form, which is equal to modulus of A into modulus of B, plus the same thing applied here. Modulus of A into B is equal to modulus of A into modulus of B. With all these terms, now we'll analyze what do we know about all these terms. We know that f of x minus L is less than epsilon 1 when this condition is satisfied. We also know modulus of g of x minus m is less than epsilon 1 when this condition is satisfied. We also know mod g of x is less than 1 plus mod m when this condition is satisfied, when the same condition is satisfied. That is why I picked up modulus of g of x, so that I can substitute for modulus of g of x as less than 1 plus mod m here. Okay, so modulus of f of x minus L is less than epsilon 1. The second term is less than 1 plus mod m. The third term, there is a plus in between, therefore plus. Plus the third term is less than epsilon 1, into the fourth term is mod L, absolute value is some number. So mod L, I will keep it as mod L. When is this condition satisfied? When does all these conditions satisfied? When mod x minus a is less than delta and greater than 0. Now there are two terms here, epsilon 1 I will take common here. So this is equal to epsilon 1 into 1 plus mod m plus modulus of m. So what do we have ultimately? Mod of f of x into g of x minus L into m. Here equal, then it became less than or equal to, then equal to, then again it is less. Which is the strict inequality I have now? It is less than epsilon 1 into 1 plus mod m plus mod n. This one more arrangement we'll have to do, because we are used to saying when x comes close to a, f of x into g of x should go close to L into m. That means given epsilon, I should find a delta such that when the distance between x and a is less than delta, the distance between these two terms should be less than epsilon. But the distance between these two terms, I have got it as less than some quantity which I am not so comfortable with. So I want to make this as less than epsilon. So what is the condition I'll have to do? I have to remove all this and bring in epsilon. So how do I do this? I will choose epsilon 1 as a number, epsilon by 1 plus mod m plus mod L, where epsilon is some given small quantity. Because this is a number in between 0 and 1, this also will be a small quantity. Now what happens? I am giving a value for epsilon 1. What was epsilon 1? We will come back here. Epsilon 1 I am being substituting, I am keeping this as it is. So we are substituting epsilon 1 as epsilon by 1 plus mod m plus mod L. So what do I have? Mod f of x into g of x minus L into m is less than epsilon 1 was here, which I am substituting from here, into 1 plus mod m plus mod L. This condition is obviously satisfied when distance between x and a is greater than 0 and less than delta. So these two conditions, these two terms will get cancelled. That is, modulus of f of x into g of x minus L into m will be less than epsilon when this condition is satisfied, so that it looks nice as a definition. That is the reason why epsilon 1 is being substituted as this quantity. So what is the ultimate thing I have? Limit extending to a, f of x into g of x is equal to L into m. This is by definition. Now we are going to the proof of 4. What is 4? Limit extending to a, f of x by g of x is equal to L by m. F of x by g of x. That is what we are doing now. Before we doing f of x by g of x, I will prove limit x tending to a 1 by g of x. F of x will take a little later. I will simply talk about 1 by g of x. We will show that when f of x is not there in the numerator, the limit also I won't take in the numerator. We will show that limit x tending to a 1 by g of x is equal to 1 by m. So that when f of x comes over here, the limit L also will come over here. So now here also I should apply the definition if I want to prove this. What should I do? Given a epsilon greater than 0, I should find a delta such that when x comes close to a, 1 by g of x comes close to 1 by m. Okay. So 1 by g of x should come close to 1 by m. That means I should talk about the distance between 1 by g of x and 1 by m. So modulus of 1 by g of x minus 1 by m. We will take the common denominator, m into g of x. So this numerator becomes m minus g of x. Now modulus of a by b is equal to modulus of a divided by modulus of b. Modulus of the numerator is modulus of m minus g of x divided by modulus of the denominator. Again modulus of the denominator, we have two parts. What is the part here? A into b. So that is modulus of first term into modulus of the second term. And modulus of m minus g of x is same as modulus of g of x minus m. If we take a minus common inside the absolute sign, minus does not matter to me. So modulus of m minus g of x is equal to modulus of g of x minus m. So divided by modulus of m into g of x. Okay. Now given that limit extending to a, g of x is equal to m. Okay. Now given some epsilon 1, I won't come to epsilon, I will start with the epsilon 1. That epsilon I will take when I have f of x by g of x. Okay. So given epsilon 1 greater than 0, any epsilon 1 greater than 0, I can find a delta 1 greater than 0 such that whenever the distance between x and a is greater than 0 and less than delta 1, we have modulus of g of x minus m is less than epsilon 1. This is, I am applying the definition for the given limit x tending to a, g of x is equal to m. Now these are quantities which I will require at the end. So we are doing it in bits and pieces. Now modulus of m is equal to modulus of, I will add and subtract g of x, which implies modulus of m, again apply triangle inequality, which is less than or equal to modulus of the first term plus modulus of the second term. First term m minus g of x, I said in modulus I can write it as g of x minus m also. Implies modulus of m, what did we do just now? Modulus of g of x minus m will be less than epsilon whenever modulus of x minus a is less than delta 1. So mod g of x minus m is less than epsilon 1 when this condition is satisfied, plus mod g of x I am keeping as it is. Or I will keep mod g of x here, I will shift epsilon 1 to that side. So I will read it from this side. What do I have? Mod g of x, this is being shifted here, mod g of x is greater than, I am looking like this, okay, mod g of x I am looking like this, mod g of x plus epsilon, mod g of x is greater than mod m epsilon 1. When it went this gone this side, it has become minus epsilon 1. So mod g of x is greater than mod m minus epsilon 1 when this condition is satisfied. Okay, now I think we should join all the pieces. I'll choose epsilon 1 as mod m by 2. So what do we have? What did we have first? Where did epsilon come? Mod g of x is greater than mod m minus epsilon 1. Now I am choosing epsilon 1 as equal to mod m by 2. So if I substitute that, mod g of x is greater than, what do I have? Mod m plus epsilon 1, mod m minus epsilon 1. So mod m minus epsilon 1 was mod m by 2, mod m minus mod m by 2, that is mod m by 2 only. For mod x minus a is less than delta 1. Or if I take the reciprocal of this inequality, this becomes 1 by modulus of g of x. When I take the reciprocal, the sign inequality gets reversed. So 1 by mod g of x is less than, when I take the reciprocal, it is 2 by mod m. 1 by mod g of x is less than 2 by mod m. What is the condition I have? Whenever modulus of x minus a is greater than 0 and less than delta 1. Now, again I will apply the definition to the same limit x tending to a, g of x is equal to m. I have not yet come to f of x, I am still in g of x only. Limit x tending to a, g of x is equal to m. There I had taken a epsilon 1, I had got a particular delta 1. Now I am taking a epsilon, given epsilon greater than 0, there exists another delta 2 greater than 0, delta 1 we have already finished. Given epsilon greater than 0, there exists a delta 2 greater than 0 such that whenever mod x minus a is greater than 0 and less than delta 2, we have the distance between g of x and m is less than epsilon into mod m square divided by 2. Now what happened? I am not taking mod g of x minus m is less than epsilon. Why is this big term we have taken? I want it at the end of the proof. That is why, that is the reason why I have taken less than, not only epsilon, epsilon into mod m square divided by 2. Okay. Can I write it as less than epsilon into any other term also? Yes, you can write. But what is the condition I have? I am given epsilon, I am finding a delta 2 exactly so that this condition is satisfied. Say you want to write this condition as epsilon into mod m square. I don't want this divided by 2. Then you might get another delta. Okay. I am choosing delta in such a way that modulus of g of x minus m will be less than epsilon into mod m square divided by 2. I would have got a delta which satisfy other conditions also. Okay. Now I had two deltas. I will take the minimum of delta 1 and delta 2. I hope you have the idea now why we take this minimum. I take the minimum so that the conditions which are satisfied for less than delta 1 and less than delta 2 are simultaneously satisfied. Okay, that means if I choose mod x minus a less than delta, the condition satisfied for mod x minus a less than delta 1 and mod x minus a less than delta 2 both are satisfied. Then when mod x minus a is greater than 0 and less than delta, the conditions which were applicable in the case of delta 1 and delta 2, which was in the case of delta 1, we had this 1 by modulus of g of x is less than 2 by mod m, that is also satisfied. The condition in the case of delta 2 is here, this also will be satisfied. Modulus of g of x minus m will be less than epsilon into mod m square divided by 2. This is the preliminary work we have done for the ratio f of x by g of x, to take the limit extending to a f of x by g of x. This is all the preliminary work we have done. Okay. After all the work, we have this important part of the proof which we have derived. Okay. Now we'll come back over there. What did we have? We had taken limit extending to a 1 by g of x. I have to prove this is equal to 1 by m. So modulus of 1 by g of x minus 1 by m. We've already simplified this and we'll apply whatever we know. This is less than mod g of x minus m. What did we have? Mod g of x minus m is less than epsilon into mod m square divided by 2 when this condition is satisfied. So mod g of x minus m is less than epsilon into mod m square divided by 2 when this condition is satisfied. Mod m, 1 by mod m, I am keeping as it is. 1 by mod g of x is less than 2 by mod m. There are three inequalities I have put here. One is equality 1 by mod m, I am keeping it as it is. Modulus of g of x minus m is less than this quantity when this condition is satisfied. 1 by mod g of x is less than 2 by mod m when this condition is satisfied. We'll simplify everything. 2 and 2 gets cancelled. Mod m becomes mod m square, that gets cancelled. So mod is cancelled. Here 2 is also cancelled. So what do I have? Modulus of 1 by g of x minus 1 by m is less than epsilon for distance between x and a is less than delta. So by definition, what do I have? Limit x tending to a 1 by g of x is equal to 1 by m. Now hope you get why we did this bits and pieces. We wanted mod g of x minus m, that is why we applied the definition. Then I took this mod g of x and simplified so that I can apply the inequality here. So these are the 2-3 pieces which we require in the proof. This is just the half of the proof. The ending important part, limit extending to a f of x by g of x. We have already done the third part. What does it say? When I have the limit of the product, it is equal to the product of the limits. So f of x by g of x, I will write it as f of x into 1 by g of x. Now this becomes a product. First function into second function. Limit of one function into another function is equal to limit of the first function into limit of the second function. What is limit of the first function? It is already given as L. What is the limit of the second function? It is given as 1 by m. Then take the product, this becomes L by m. So limit x tending to a f of x by g of x is equal to L by m. So that was the last fourth part we had, so that it is satisfied. Limit x tending to a f of x by g of x is equal to L by m. This completes the proof of algebra of limits. These are in 4 parts. Each part is done in a different way. each part. The epsilon delta definition is also applied in a different way. Few places we have taken as epsilon 1, few places we have taken as epsilon, in other place it is epsilon 1 which is less than 1 also it is being taken. So as required in the proof, we have changed the epsilon and delta very minutely, so that at the end we are left with one delta and one epsilon. I hope you have understood the proof of all these 4 parts: addition, subtraction, product and the ratio of the functions, how to take the limit.